Greetings, this is Advait Karnad, and today I'm going to highlight the actual implementation in Unity for the ocean simulation project, along with buoyancy interaction, the use of particle systems to simulate rain and clouds. So here we have the result of a few days of development using the game physics concepts that I have highlighted in the previous videos, and we have used Unity for this project, and we have implemented ocean wave dynamics, which are waves basically. And along with that, we have used an asset of a ship to highlight how buoyancy interacts with those very waves. And further on, we have also implemented rain as a particle system along with fog or clouds as a particle system. So let's begin with the first main element in game physics that we want to implement, which is waves. So waves are basically going to be implemented as a mesh, which has a different vertical height at each position based on what point the wave, uh, based on what point that particular wave is in. So here we have an object. So this is the Unity window. On the left side, we can see the sample scene. So here we simply need to create an empty object. So by right clicking, we create an empty object here, and once we create the empty object, we can name it waves. So here I have already done that. So we have a waves object. So when we make a waves object, we have an empty, we have none of these components which are added here. We have an empty uh, object here. So here what we can do is we can add a component which is a C# script. So here I've already done that. Let's open up the waves script and we can understand the code in detail. So once I open up the wave script, here we can see the wave. So the main first and foremost, we need to actually make the base mesh, which is simply a plane. And in the plane, we have a particular size, which we determine as the sort of resolution of the mesh. So the size dictates how detailed the mesh is and how big it is. So here we have a public integer called size, which dictates how many points there are on the x and the z axis. We have a UV scale. UV scale is basically used to highlight how visible the waves need to be. Further on, to aid the waves and how they can be overlapped over each other, we have an octave object. Here we have a structure called octave, which I'll explain further. And so on and so forth. We have a few utility fields for a player interaction. This can be skipped for the game physics implementation. Further on, to implement the mesh itself, we need a mesh filter, a mesh itself, and a mesh collider. These are all components which are protected within the class. So here in Unity, we can see that if we click on the waves object, we have what is known as a mesh renderer. So a mesh renderer allows us to render the actual wave. So what we can do is we can create a material for the water and assign it to this mesh renderer so that the wave actually has a surface to render. Otherwise, if we don't do this, it'll only look like a blank pink default color. And instead of that, we don't want that. We want it to look like actual water. So we use a shader graph here. So what we are simply doing in the start method is we are initializing the mesh as a basic mesh, and we are making its vertices and triangles and UVs, and we are also referencing and adding the component of the mesh filter to the script so that we can reference it. Now we come to the actual mesh handling. So this method here, generate words, is called here in this particular line of code. So what does this generate words do? So generate words means we are actually making the vertex positions based on a particular algorithm. So here we have a simple logic script where we use a vector 3. A vector 3 is a vector with 3 components. So it has x, y, and z. So we want this to be as big as size plus 1. So because a vector array needs to be 1 more than the size required. So we have size plus 1 times size plus 1. So we have in the x direction we have size plus 1 times the z direction size plus 1. So we have a square. We can make this as complex as we want. If we want a rectangle, we can change these fields as per necessary. For this demo, we will simply use a simple square. So then we create each vertex. So for every x in this particular array less than size, and for each of those x we'll have a particular z. So we are going based on each column, we are going into each row, and then for every index of x and z we create a new vertex at that particular x position, at that particular z position, and at 0 height. So x and z here are world positions also. So what is this index? Let us have a look at that. So when we generate a mesh, at every row we need to once we reach size, we need to go to the next column. Once we finish the particular column, and we need to move on to the next column or the next row. If you're looking at from the x direction, you'll have row. From the z direction, we'll have column. So what we can do here is this particular method is used here. So we have an index calculator. So we simply return x times the size plus 1 plus z. So we calculate how many rows have passed, and we also add the column within that row to this method. So this simply returns the index 2D index array position here to words. Words is basically the array that holds this. Similarly, we have the generate tries. So vertices are the points themselves. The tries or the triangles are the faces that are enclosed within those vertices. So for every tile, we have two triangles. So a tile is basically a square. So a square can be made of two right triangles. Okay, and so for each particular tile, we need six vertex. We need a set of six vertex. So we need one. We need 1, 2, 3, 4 for uh, one triangle, and for the other we need only two more, so we have six in total. So 3 plus 3 can also be a way to look at it. So what we need to do here is we have a algorithm which is called a mesh generator here. It simply takes in an x and z position, and it goes through each of the six of the tiles and generates each face by themselves. So if I can have a better demonstration, I will put it in to this part here. So we can have a look at the actual way this is calculated. So further on, we need to also calculate the UVs. UVs are basically the ultraviolet scales. So for every vertex, we need to calculate the UV, and for this, we simply use the UV scale. So this dictates how the render pipeline works, and at what point what vertex needs to be rendered. So this is how a basic mesh is handled. Now let's come to the core part of the ocean simulation. So for an ocean, we simply need a the basic premise is a wave. So wave can be any wave. It can be a sine wave or cosine wave. For this implementation, we'll use cosine waves as a base. So the y coordinate at every x and z needs to be a cosine function. However, if we simply use a cosine function, it will be very simplistic and it will only give us a vertical displacement which is very uniform. We don't want uniformity because waves are not uniform in the real world. So we need a little bit of variance, and we need what is known as constructive and destructive interference of the waves. So here we have a method here within the void update. So update is called every frame. So at every frame, what we get is we get the vertex data, which is the base data of a plane mesh, and we iterate through each x and z. So for every point, every x in the every vertex position of x, and for every z position of that x, we uh, run this particular script here. So what this simply does is it assigns a variable y to 0. So this is the basic height. Then we have a direction vector which is also put into 0 uh, by default. Then what do we do is we iterate through what are known as octaves. So octaves are basically the constructive interfering of multiple waves. So one octave is one wave, a second octave is a second wave. So in the real world, there are multiple waves that collide with each other and form the real interface of the surface of the water. So here we have what is known as alternate waves. So alternate is basically used as a boolean here. So here we can see the structure of octave. So we have the speed of that particular octave, the scale, that is how big the particular octave needs to be compared to the rest. We have a height, that is the maximum height of each wave in that octave, and we have an alternate, which is simply a boolean variable. So here we simply check whether it's alternate or not. Based on that, we put a different uh, formula for the height variance. So we use what is known as Perlin noise. Perlin noise is a function which takes in an x and a y, and it returns a value between 1 and 0, and this 1 and 0 is a float value. So when this is done, we get a uniform noise pattern. So we can use this and we can multiply this x times the scale and the time that has passed in the scene and the speed of each in the x and the z coordinate. And using this, we can get a Berlin noise that moves over time. So this time helps us move the map of the Berlin noise. So here we can see the Berlin noise itself moves, and simply we need to add that Berlin noise to the height of the octave. So this is a general implementation of height. Similarly, what we can do is instead of the Perlin noise being scrolled, right, we can keep that Perlin noise static, and instead we can change the cosine of that. We can change y by a cosine of that Perlin. So the Perlin noise that is generated by this line of code is given as a parameter to the cosine function here, and it gives a more it gives a larger variance in the waves and a different look to it. So these two different approaches, when mixed together, gives a more realistic approach. Now, when it comes to Gerstner waves, which are the most useful in terms of game simulation, uh, the same pattern is used. However, there we need to also take care of x and z. So here we have simply, for the sake of the demo, we are not going to move the x and z very much. So I've simply taken the direction which is still at 0 and 0, and I have added that to a displacement of x and displacement of z variable, and added it to the x and z. When, if required, we can simply use the Gerstner wave algorithm and add it here for the x and z also. So once that is done, we simply recalculate the normals, and we have the mesh itself. Now, this is simply a follow player script that I've added, which allows the player to move around. So let's have a look at the final result of the waves. So if I click here on play, we have this. So this is simply an asset of a ship, and I have basic player controller which is bound to my keyboard. So here you can see that the waves actually move around, and along with the shader graph that I have made, we can use normal maps to highlight lighting, and also color the scene based on the height of the wave. So here you can see there is a different shade, a lighter shade of blue and a darker shade of blue, that's done using a shader graph which takes in the position. So now that the waves are done, let us have a discussion of the buoyancy. So buoyancy is used here. As you can see, the ship floats, and it floats very dynamically. You can see that the when I move, it actually responds to the waves going up and down. What kind of a script is required to do this? So here we can see that if I stop the scene, here you can see the boat itself. So this is the asset that we have here, and we can have a look at it. So this asset is a boat. So for anything that needs to float on water, the main thing which we need to handle is the volume of that object. So a volume is what makes and breaks the buoyancy force required for that object to float. So if we know the formula of buoyancy, it is F is equal to rho Vg, where rho and G are basically constants in a scenario. So rho depends on the water and the waves. So that can be something that is treated as constant in a scene, which is simulated like this. G is obviously a gravitational constant that can also be treated as a constant. So what really changes is the volume that is immersed in the water. So here we have a what is known as a floating script that I've made. So it takes in the if we look at this player object is the object that we have implemented here. So within the player object, I have this asset of the boat. So this is simply a empty object here. In that we have these game objects. So these game objects are used to find the bounding box of the object. So the boat itself, so we want the boat to sink up till this point. So we use this height of the of these four game objects, which are simply anchors which are used for the back end of the scene, and we can set them at this particular position here. And once we find the positions proper, we can use what are known as a float script. So here we have a boat control script which allows us to control the boat itself, and we have a floating script. So here you can see I have in the floating script, I have floating points. So I can have as many points as I want. For this particular asset, I've simply used 4 ones. And each of these game objects are fed as a transform. So it takes in the position of these as an input, and based on that, it can calculate how much of the boat do we want to actually be in the water in the scene. So let's have a look at the floating script. So in the floating script, we have a few constants like air drag, water drag, whether the boat has to be affected by the direction of the wave or not, and whether the boat wants to be attached to the surface. So this is very useful for whether, let's say I have a very fast speedboat, right? And given that we are using force, so if it's going very fast, it might fly off the wave, and it might cause unwanted behavior. So this can be used in such cases. In our case, we are not very concerned with that part because our ship is quite slow. It is a old sailing ship. In case we use a speedboat which has a faster player control motion, we might require that. Then we have a transform, which is basically these float points here. So these 4 float points are an array, and each of these positions are put here as a transform array. Similarly, we use the protected rigid body and a waves component. Now this is important because this very waves script that is here, so we have an object of waves right here, this particular waves object, that is referred as a component here. So this is what is used to find the water line at that particular point of time using the mesh of the waves. So what this simply does, this entire code is it takes in the mesh data at a particular point of time from the waves component, and it compares the amount that is inside the water versus outside of the water when compared to the green spheres. So the line is what matters. So if I run this now, it will be better to explain while it's running. So if I go into scene here, you can see that there are red and green gizmos. So these are what are known as gizmos, which can be used in the scene. It will not be shown in the game, but it will be seen here in the scene editor. So the green spheres basically are the line for the object. So they determine the line perpendicular to the object's normal. So the weight is acting perpendicular downward to this plane, which is highlighted by the 4 points. Whereas the red cubes are what determine the mesh of the waves. So as you can see, the red cubes actually perfectly follow the waves and the interface of the waves, whereas the green lags behind or sometimes even floats above based on what part of the wave uh, is being traversed at that point of time. So here we have a central cube which takes in the mesh data of all of these 4 cubes and calculates a normal vector based on an algorithm, and this normal vector is used to apply a force. And based on the difference of the positions of these spheres, so the y position of these spheres from the cubes, we can find the amount of force we require to be put on this particular point. So in the case that we have an odd number of points, let's say I have one here and two behind, that's when things like rotational torque come into effect. So the force is acting at each of these points because they are uniformly distributed. You're not seeing any rotational torque right now. But if I were to remove one of them and center them in or position them in a very non-uniform manner, we can see weird effects happening. So this is very useful for objects which are not really stationary on water and have motion to them, and they are not uniform in their mass distribution or geometry. So that's how buoyancy is done. So the script and all of this is available in the description through my GitHub. Uh, I will not be going into the nitty gritty of the code because the video will go too long. Finally, we have the atmospheric elements, which are the rain and the cloud. So rain and clouds are simply particle systems. So here we can see there's a cloud system. So there's a particle system here. So we can see here. So all of this is a particle system. When we zoom in, we get to see the actual effect from the board. So this is nothing but a bounding box, a very large bounding box at that, which extends from the sky all the way down to the ocean. And at each particle, there is a texture and a normal map that is put. So here you can see that we have this particle system here. So we have the bounding box in the shape here. If we look at it, this is the bounding box of the rain of the cloud system. So this is a box volume. Along with that, we have an emission spectrum, which at every time step that goes forward, 100 of these particles have spawned and they die away in quite a quick time. So within 15 seconds, 20 seconds, they die out. So they'll fade in and out of existence, and within this time, the texture that is shown at each point moves a little bit. So velocity over lifetime can be used to change their position. Like you can see, this particular particle has moved from this side to this side and it's fading away. So this gives a very realistic looking fog effect. And when made very dense, like let's say I want actual cloud cover on top, I can simply make this bounding box smaller and make this a lot more dense, because right now the transparency of the texture is high. So if I reduce the transparency, then it will become like clouds. Now this is what is called a volumetric particle effect, because it's not moving around. It is based on a bounding box, and it remains stationary. So that's what a volumetric particle system is known as. So it's less moving and it's more for the atmospheric look. Whereas rain, if I spawn it in, if I stop this and I'll simply do the rain. So the rain, you can see, are simply lines that fall down. So these are all line particles, very stretched in the y direction, don't have much depth or thickness in the x and z, and they simply fall down from a large area. So if I look at the shape here, you can see the bounding box is very far up. It's not really in the play area. And from here, objects, the particles spawn in and they fall down. So this is how rain can be simulated. So this is known as a dynamic particle system because it moves. The particles, the motion of the particles have more preference, more importance than the volume of the particles. So when combined, all of these effects, when they are combined together, we get the final result that is very atmospheric in nature. So if I can go here to the game, I click on maximize on play so that the effect is quite good. So here we have the final product. So we have a player controlled ship which moves around, and it has a nice fog effect even around the waves where the wake of the ship exists. Then we have the waves which are dynamic, which move around, and we also have the fog, which is if I go on to a wave, you can see here there is all the fog in the atmosphere along with the rain that's falling. And then we also have normal maps in the shader which allow the water to reflect like this, very beautiful looking water. So all of these effects together can be used to make a ocean simulation of a stormy sea. So thank you for watching, and thank you for watching the series if you watched it all the way. Thank you.